Have you ever stopped to think about all the amazing things happening around you right now? I mean, really think about it. The screen you're reading this on is powered by a tiny, controlled chemical reaction inside a battery. The air you're breathing is being used by your body in a fantastic series of reactions to give you energy. Even the simple act of baking a cake or a piece of toast browning is pure, unadulterated chemistry in action. It's not some scary, complicated thing that only happens in a laboratory with bubbling beakers and people in white coats. Chemistry, and specifically chemical reactions, are happening everywhere all the time. They are the engine of our world, the ultimate cosmic dance. From the fiery heart of the sun to the quiet rusting of a bicycle left in the rain, our universe is one giant, continuous chemical reaction. Think about it. A plant growing is using sunlight to power a chemical reaction called photosynthesis. A firefly glowing in the dark is creating its own light through a cool reaction called bioluminescence. You don't have to be a scientist in a lab to see chemistry. You just have to look around. It's in your kitchen, in your backyard, and even inside your own body. It's the science of stuff and how stuff changes into other new stuff. The goal here isn't to make you a world-famous chemist in 10 minutes, although that would be pretty cool. The goal is to pull back the curtain and show you that you're already an expert observer of chemistry. We're going to explore what a chemical reaction really is, how to spot one, and why they are so incredibly important to, well, everything. So get ready to put on your imaginary safety goggles, because we're about to dive into the world of molecules and atoms. We're going to see how they break apart, shuffle around, and form new partnerships. All right, let's get right to it. What in the world is a chemical reaction? Put simply, a chemical reaction is a process that changes one set of chemical substances into another set of chemical substances. It's like taking a pile of Lego bricks that are built into a little car and a little house, breaking them all apart, and then using those exact same bricks to build a big spaceship. You haven't created or destroyed any bricks. You've just rearranged them into something totally new with different properties. The car and house are gone, and now you have a spaceship. In the world of chemistry, we call the starting materials, our Lego car and house, the reactants. They are the ingredients you start with before the change happens. When you mix baking soda and vinegar, you start with a powder and a liquid. But what you get is a fizzing foam of carbon dioxide gas. The gas is a completely new substance that wasn't there before. Now, this is different from a physical change. A physical change is when a substance changes its form but not its chemical identity. Think about an ice cube melting. You start with solid water, ice, and you end up with liquid water. But in a chemical change, like burning wood, you start with wood and oxygen, and you end up with ash, carbon dioxide, and water vapor. You can't just unburn the wood to get it back. So, how does this atomic shuffle actually happen? It's not magic, it's science. For a chemical reaction to kick off, a few things need to happen. First, the reactant particles, the atoms or molecules, have to actually find each other. They have to collide. You can't bake a cake if the flour stays in its bag and the eggs stay in the carton. They have to be mixed together in a bowl. In chemistry, this means the reactant molecules are zipping around and bumping into one another. The more they bump into each other, the more chances they have to react. But just bumping into each other isn't always enough. The molecules have to collide with enough energy to get the reaction started. This minimum amount of energy is called the activation energy. It's like trying to push a big rock over a hill. You have to give it a good, hard shove to get it to the top of the hill. Once it's there, it can roll down the other side all by itself. A match won't light itself. You have to strike it, providing the friction and heat, the activation energy, to start the chemical reaction of burning. On top of that, the molecules have to collide in the right orientation or the right position. Think about trying to fit a key into a lock. You can't just jam it in any which way. Molecules are the same way. They have specific shapes, and for their atoms to form new bonds, they often have to collide at the perfect angle, like two puzzle pieces clicking together. Once these conditions are met, collision, sufficient energy, and correct orientation, the old bonds break and new bonds form. The atoms rearrange themselves into the more stable configuration of the products. Chemical reactions come in all shapes and sizes, but chemists like to group them into families to make them easier to understand. Think of it like organizing music into genres like rock, pop, or classical. First up is the synthesis reaction. This is like two people deciding to become dance partners. Two or more simple substances combine to form one, more complex product. The general recipe is A plus B yields AB. A great example is when iron reacts with oxygen in the air to form rust, which is iron oxide. You start with two separate things and end up with one combined thing. Next, we have the opposite, the decomposition reaction. This is when our dance partners decide to go their separate ways. One complex substance breaks down into two or more simpler substances. The recipe here is AB yields A plus B. A fantastic example happens when you run electricity through water. The water molecule splits apart into its simpler components, hydrogen gas and oxygen gas. Then there's the single replacement reaction, which is like someone cutting in on a dance. In this reaction, one element swaps places with another element in a compound. Imagine you have a solution of copper sulfate, which is blue. If you drop a piece of solid iron, like a nail, into it, the iron is more reactive and will kick the copper out of its partnership with sulfate. Finally, let's talk about the double replacement reaction. This is when two couples on the dance floor decide to swap partners. Two compounds react, and the positive and negative ions of the two reactants switch places. A classic example is mixing a solution of potassium iodide with a solution of lead nitrate. Both are clear liquids, but when you mix them, the potassium and lead swap partners, forming a brilliant yellow solid called lead iodide. You don't need a fancy lab coat and $1 billion laboratory to be a chemist. In fact, you're probably performing chemical reactions every single day in your own kitchen. Cooking is chemistry you can eat. When you bake a cake, you're not just mixing ingredients. You're initiating a whole series of complex chemical reactions. The baking soda or baking powder you add is a base. When it gets mixed with acidic ingredients like buttermilk and then heated, it undergoes a decomposition reaction. This reaction releases bubbles of carbon dioxide gas, which get trapped in the batter and make the cake light, fluffy, and delicious. That's a chemical reaction making your dessert better. Ever seen an apple slice or a banana turn brown after you've cut it? That's another chemical reaction right on your cutting board. It's called enzymatic browning. When you cut the fruit, you break open its cells, releasing enzymes. These enzymes react with oxygen from the air and substances in the fruit called phenols. This reaction creates new molecules that have a brownish color. Let's not forget the classic science fair volcano mixing baking soda and vinegar. This is a fantastic acid-base reaction. Vinegar contains acetic acid and baking soda is sodium bicarbonate, a base. When you mix them, they immediately react in a double replacement reaction that produces carbonic acid. But carbonic acid is very unstable, so it instantly decomposes into water and carbon dioxide gas. Even the simple act of frying an egg is a masterclass in chemical change. A raw egg white is mostly made of proteins, specifically a protein called albumin, which are all folded up in specific complex shapes and floating in water. When you add heat, you provide the energy to break the weak bonds holding those proteins in their folded shapes. The proteins unfold and then tangle up with each other, forming a solid, white, interconnected network. This process is called denaturation, and it's an irreversible chemical change. So, you're surrounded by chemical reactions, but how can you be sure one is actually happening? What are the clues? Being a good scientist is kind of like being a good detective. You really have to look for the evidence. Luckily, chemical reactions often leave behind some very obvious signs that a change has occurred. One of the most common and, honestly, most exciting signs is a change in color. We saw this with the browning apple and the brilliant yellow solid that formed in the double replacement reaction. When you see a substance change color without you adding any dyes, that's a strong hint that new molecules with different properties have been created. Another huge clue is the production of a gas. Think back to our baking soda and vinegar volcano. All that fizzing and bubbling is a dead giveaway that a gas is being produced. You can see this when you drop an antacid tablet into a glass of water. The tablet fizzes as it dissolves, releasing carbon dioxide gas. This is actually different from boiling water, where you're just turning liquid water into gaseous water, or steam. Have you ever used a chemical hand warmer on a cold day? You snap that little metal disc inside, and the pouch gets warm. This is a sign of an exothermic reaction, which is a reaction that releases energy, usually in the form of heat or light. But hey, the opposite can also happen. An endothermic reaction absorbs energy from its surroundings, making things feel cold. Some instant cold packs work this way. When you break the inner pouch, chemicals mix and pull heat from the environment, making the pack feel icy. Finally, a fourth big sign is the formation of a precipitate. That sounds kind of fancy, but a precipitate is just a solid that forms when you mix two liquids together. We saw this with our double replacement reaction, where mixing two clear liquids magically produced a solid yellow powder, the lead iodide. This solid is precipitating out of the solution because it's not soluble, meaning it can't dissolve in the liquid. So we've seen that chemical reactions are cool, but why do they really matter? The simple answer is, they make life and our modern world possible. Let's start with you. Every breath you take, every move you make, every thought you have is powered by chemical reactions. The process of respiration in your cells is a complex series of reactions that takes the food you eat, like glucose, and the oxygen you breathe and converts them into the energy your body needs to function. Beyond our bodies, chemical reactions are honestly the foundation of our entire civilization. Think about agriculture. The invention of the Haber-Bosch process, a chemical reaction that combines nitrogen from the air with hydrogen to make ammonia, was a total game changer. This ammonia is used to make fertilizers that have allowed us to grow enough food to feed billions of people. The plastics in your computer, the medicines that cure diseases, the fabrics in your clothes, and the gasoline that powers our cars are all products of carefully designed and controlled chemical reactions. Nature itself is a grand chemical engineer. The most important reaction on our planet is arguably photosynthesis. Plants, algae, and some bacteria use energy from sunlight to convert carbon dioxide and water into glucose, their food, and oxygen. This reaction not only creates the basis for most food chains on Earth, but also produces the oxygen in our atmosphere that most living things, including us, need to breathe. Chemical reactions also drive geological processes, like the formation of caves as acidic water dissolves limestone, and the carbon cycle, which regulates our planet's climate. From the grand scale to the small, reactions are everything. They clean our world through detergents that break down grease and grime. They power our exploration of space with rocket fuels that are the result of powerful exothermic reactions. They allow us to create new materials with incredible properties, from super strong alloys for building jets to semiconductors for building computer chips. Understanding how to control these reactions allows us to solve problems, innovate, and improve our quality of life. We have covered a lot of ground in a very short time. So let's slow down and put all the key ideas together in one place. Think of this as your handy cheat sheet for understanding the amazing world of chemical reactions. First and foremost, remember what a chemical reaction is? It's a process where starting substances, called reactants, are transformed into new substances, called products, by rearranging their atoms. You're not making or losing atoms, just shuffling them around into new combinations, like building something new out of the same old Lego bricks. Next, remember the secret recipe for making a reaction happen. The reactant particles must collide with each other. They have to hit each other with enough energy, the activation energy, to break their old bonds. And they often need to collide in the correct orientation, like a key fitting into a lock. Don't forget the main families of reactions. We have synthesis, where simple things combine to make something more complex. We have decomposition, where one complex thing breaks down into simpler parts. There's single replacement, where one element cuts in and swaps places. And finally, there's double replacement, where two compounds swap partners. And of course, be a good detective. Look for the 4 key signs that a reaction is happening: a change in color, the production of a gas, like fizzing or bubbles, a change in temperature, whether it's getting hotter or colder, or the formation of a precipitate, which is a solid forming from liquids. So there you have it. Chemical reactions aren't some mysterious force hidden away in a secret lab. They are the very fabric of our existence, They are the sizzle in the pan, the fizz in your soda, the breath in your lungs, and the light from the stars. The next time you cook a meal, light a match, or even just watch a leaf change color in the fall. Take a moment to appreciate the incredible chemistry at play. You are witnessing the breaking of old chemical bonds and the formation of new ones. You now have the knowledge to be a reaction detective, spotting the clues of chemical change all around you. Is it getting hot? Is it bubbling? Did the color change? You know what these signs mean. They mean atoms are on the move, creating something new. Science is all about curiosity. It's about asking questions and looking for answers. So go forth and react. Be curious. Observe the world around you. Mix that baking soda and vinegar, with permission, of course. Notice the chemistry in your kitchen and in nature. Because understanding science, even just a little bit, doesn't take the magic out of the world. It adds to it. It allows you to appreciate the elegance and complexity of the universe on a whole new level. It's an amazing world out there, full of incredible, non-stop chemical action. Science is for everyone, and now you're a part of it. How cool is that?